Welcome to the Enhancing Clinical Practice and Outcomes stream at SNOMED CT Expo 2025. Thank you to FAST for sponsoring this session. My name is Liara Tatina, and I'm the Customer Relations Executive for Asia and Pacific and Global Education Lead at SNOMED International. I'll be your moderator for the session today. We'll address all the questions at the end of the presentation. For our online audience, please use the Q&A button to submit your questions to the presenter. For those attending in person, feel free to use your microphone that's provided in the room here when the time comes. And it's now my pleasure to introduce Stijn De Saeger from ibis.ai, apologies for my pronunciation, who will be presenting NLP OMOP Transforming Clinical Narratives into Actionable Data. Stijn, over to you.
Thank you. So my name is Stijn De Saeger. I'm the co-founder and tech lead of ibis.ai. And the title of this talk is called NLP to OMOP, Transforming Clinical Narratives into Actionable Data. And this talk is actually an experience report for the NLP to OMOP project. And this project originated in 2023 with a government-funded call for innovative data projects that do something with healthcare, data reuse, and data interoperability. And this is in the context of the data capabilities calls that were mentioned by Minister van den Broeke in the previous keynote, right? And so the partners for this project are 4 Belgian hospitals, AZ Clina, AZ Delta, Azorg, and AZ Ostende, and 2 technology partners, so Edens Health and ibis.ai. And so throughout the project, we had a strong focus on building generic solutions and reusable technologies, because the whole purpose of this thing is to do something with data reuse and interoperable data. And so that means that whenever possible, we try to abstract away from hospital-specific details around their EHR implementation. And at the same time, again, following the suggestion of the keynote, we fully embrace open source technologies. So we don't aim to reinvent the wheel. We reuse open source models and technologies whenever available. And at the end of the project, all the technologies and the tools, the solutions developed will be made available under an open source license to the public and to the community. So what is the mission? What are we actually doing here? The one thing that these 4 hospitals basically have in common is that they all have an OMOP CDM instance running on-premise in the hospital. And so the OMOP Common Data Model, it's the Odyssey community's standard data model for turning structured data that might live scattered throughout various data silos in each hospital, turning it into fair data, right? So findable, accessible, interoperable, and reusable data, such that it can be leveraged in real-world evidence studies, clinical data registries, national data registries, and various other things. And so the point of this specific project is that it basically inspired by the observation that the vast majority of all actionable data, clinical information, only really exists as in unstructured text, right? So this information, unless it's displayed on a computer screen somewhere for a human user, is not actually reusable or actionable in the vast majority of cases. Like the running example or the guiding example throughout this project has been a study proposed by AZ Clina into post-operative infections, right? And so the structured data inside the OMOP CDM can definitely tell you which patient received which treatment, which operation. But whatever complications that might have arisen in the context of this operation is not typically accessible in structured data, in structured form. And so this needs to be found in clinical text. So the aim of this project is to extract SNOMED CT concepts from unstructured clinical text using modern NLP and AI technologies, and to insert this or ingest this in the OMOP CDM so that it can be used to complement or supplement the data that's already there for analysis. And so structuring to SNOMED CT, what does that mean exactly? Turns out that means quite different things to different people. So just to give a short fictional example of a clinical narrative, the thing that says that during the examination, the patient reported no significant chest discomfort at rest, but described occasional shortness of breath when running, especially in cold weather, but denied wheezing, cough, or sputum production. So probably not surprising to anybody in the room here. If you were to translate this into SNOMED, sorry, it would look something like the thing on the right. So it's an ECL query that it aims to be a faithful representation of the information in that text, right? It's a bit big, so I try to summarize some of the main points here. So it talks about an examination context that has a patient as a subject, right? There is a mention of chest discomfort as a finding that is absent. And there's a temporal qualifier saying that, well, this chest discomfort happens at rest. There is a finding for dyspnea with additional qualifiers, like saying the frequency is occasional, the trigger is exertion, namely this act of running. And there's an environmental context, or temporal context, if you will, when there's cold weather. And additionally, wheezing, coughing, sputum production is found to be absent. Now, it may come as a surprise to people in this room, but if we speak to clinicians on the field, healthcare professionals, when they think of structuring something to SNOMED, this thing on the right here, it's not what they're thinking of. It's not what they imagine. And it's not necessarily more actionable than the text that generated it. For those clinicians in the field, structuring something to SNOMED means deriving a list, preferably a quite short list of singular atomic SNOMED concepts, pre-coordinated concepts, that they can work with, they can store in their EHR, and they can find later on. So something like hashtag dyspnea, maybe, if you will. In our experience, that seems to be the main consensus in the field. Yeah. So it's a bit of a contrived example, but the larger point it tries to illustrate is that translating text into a structured representation in itself does not reduce complexity. It mainly just reformulates it, repackages it. It does not automatically turn it into something that's actionable, right? And so when healthcare clinicians, healthcare professionals tell you they want to structure something into SNOMED, they want to translate something into SNOMED, oftentimes what they mean is they don't really want translation, they want summarization, they want salience, they want a short overview of what the thing they're looking at. And so the current best practice in EHRs today is coding at the source, where the clinician will actually have a custom idiosyncratic set of SNOMED CT ref set with concepts. And this set can be different per hospital, can be different per specialism inside the hospital, even per physician, right? So when there's a bit of a caricature drawing there of an EHR page where there's a drop-down list with available pre-registered SNOMED concepts for this specific clinician, right? As you might imagine, this severely limits data reusability, data interoperability when everybody is using their own idiosyncratic subset of SNOMED. And more importantly, we think, you also have the problem of the unknown unknowns, right? There's really no good way of knowing which potential SNOMED concept will be relevant in the future for some future RWE study, for some future research question. So every hospital, every organization needs to find this balancing act of finding a solution that's manageable, that's practical for the people in the field, and at the same time, maximizing potential reuse in the future. We think this is a very hard balancing act. So the solution that we explored in this project is something we call late structuring, or maybe a better name would be lazy structuring, namely to only structure something into SNOMED CT when you know what it is you're looking for, and only structure the thing that you're looking for. So only whenever there's a concrete research question, there's a concrete target application or target question that you're looking to answer through SNOMED, will you go out and structure this data? And this by itself raises a few other interesting problems, namely that you have to be able to, on the spot, come up with new, potentially quite dynamic SNOMED concepts, ref sets, concept sets. And this ability needs to be available to people who might not necessarily be SNOMED experts, right? Who the people in the field, clinicians, need a flexible way of working with this. Just a quick drink, if that's okay. Much better. So for this last part of the point, this a tool that supports users for building these flexible concept sets, we built something called SNOMED Query Builder, or affectionately called SNOCube. And I think I'd like to explain what that looks like first. So it's a web application that allows users to build SNOMED concept sets without necessarily having to know a whole lot about SNOMED. And the entry point into it is a semantic search application where users can, in natural language, describe some clinical condition or some clinical picture that corresponds to the phenomenon they're looking to investigate. And behind the scenes, this description will be matched using an AI model, will be matched against all known SNOMED concepts. And all the SNOMED concepts that match this description are displayed on the screen as a graph. So the graph you're seeing there, all these nodes in the graph represent SNOMED concepts. The gray boxes are clusters of densely connected concepts. And this graph is interactive, right? So users are able to flexibly include or exclude certain concepts into this concept set, depending on the attributes they have or relations to other concepts. So we call these query sketches because the SNOMED concepts that end up remaining in this set will become queries for investigating EHR data, patient data. This graph thing, underlying the graph thing, is a fairly complex ECL query that is built by the tool. And you can have multiple views on this ECL query. So this is another view on the same query. People who have children, young children, that are a bit computer savvy might recognize this layout. This is like a Scratch style interface where people can essentially, at the similar way to the graph view, mold and sculpt a set of SNOMED concepts by dragging and dropping blocks. And underlying, the app will keep a consistent view on an ECL query that represents this research question that you're looking at. And then finally, once you have built this concept set of SNOMED concepts, you're now ready to start querying your EHR. So this is the whole notion of late structuring, right? Once you know what you're looking for, only then will you go and structure text into SNOMED concepts. So the web page shown there on the left-hand side is a small button, and this is really for interactive use. So users can start querying the database or querying the patient population with this concept set, but also with just natural language text queries. And the idea there is to have like a rapid feedback cycle. You would get interactive results quite quickly to see what type of patient records match this query. And then on the right-hand side, you have this Into OMOP button. And this Into OMOP button basically repeats the same query, only it scans the entire patient population, and it retrieves potentially thousands or tens of thousands of matches that are then at that point no longer displayable in the interface, but then just go straight into OMOP. OMOP has this NLP node NLP table, which is specifically built for storing results of some NLP extraction algorithm. And as such, it contains meta information like a confidence score, et cetera, to indicate that the SNOMED concepts there have a different ontological status, right? They have not been validated by human users. It's just an automatically extracted result. So maybe briefly discuss a little bit the architecture, the underlying model. So everything starts with a query from SNOCube. And whenever I say query here, you have to think SNOMED concepts or definitions, descriptions of SNOMED concepts. So the query comes into a retrieval module that consults a large vector database of pseudonymized and chunked EHR documents. This retrieval model then sends candidate matches to a re-ranking model, and then depending on the outcome, sends these results back to the SNOCube web app, such that the user can interactively inspect the results, or it sends the results straight into the OMOP CDM with some additional post-processing. So this vector database is essentially the big data backbone of the entire system. And it consists of chunked and pseudonymized EHR documents. So the whole process of pseudonymization, we use an open source tool called Deduce. And then all these documents are chunked and stored as pre-computed vectors in this vector database. To give some idea of the scale, in AZ Kliniken, one of the hospitals in this study, The vector database contains data for some 92,000 unique patients. 3.7 million documents have been indexed for a total of a bit more than 100 million of these chunks. So it's already a scale that is usable. You can derive some statistically significant results from that. It's not longer a toy implementation. Then this retrieval module is there to retrieve candidate chunks from the vector database based on multi-vector similarity to the pre-computed chunk vectors in the database, right? The algorithm we use for this is Colbert V2, which is a state-of-the-art neural information retrieval algorithm. It basically works by computing the sum of the maximum similarity of all the token embeddings of the query against all the token embeddings in each chunk in that database. And it tries to, I mean, it works really hard to try to do this in an efficient way. And the base model that we use for training this Colbert model is, again, an open source model called BioLord, which we'll return in the next section as well. So then these candidate matches that are generated go into a re-ranking module. And this re-ranking module, again, is a model that is specifically trained for this purpose in each hospital. So in each hospital, we train both the retrieval model and the re-ranking model for this specific purpose. And this is, well, it's used to rescore candidate chunks based on the in-context similarity to the query, right? And this is a cross-encoder architecture that's trained as a binary classifier on some 4 million concept text pairs, so text snippet pairs. And so for each of this pair of a concept and a text, basically the sample tries to answer, or the model tries to learn whether this text chunk is actually about this concept or refers to this specific SNOMED concept over there. And then this is a bit of technical detail, but we found it works actually a lot better when we use the cross-encoder model as a teacher model for training the Colbert model. So the order of training is actually reversed for training the Colbert model with some ranking objective. So where you train a Colbert model to try to reproduce a ranking induced by the scores of this re-ranker model. Then when we go into OMOP CDM, or before we go into the OMOP CDM, there's a bit of post-processing to make the results even more usable or reusable, if you will. A big one is negation detection. So oftentimes these models the only thing that these models have been trained is to detect whether a certain piece of text is about a certain SNOMED concept, but sometimes these appear in a negation context. And so when something says, well, patient shows no significant signs of this or that, then you want to detect that this is basically negated, because this makes downstream analysis in OMOP CDM quite a bit more useful. Right? A similar thing happens with experiencer detection. Basically, it's the problem of trying to find out whether a certain SNOMED concept applies to the patient or somebody else in the patient, like typically family members. And there is also a quite crude way of extracting the event date from the text or from these snippets. This basically try to figure out whether there's a date that's being referred to as the onset of the condition that we're looking for. And it backs off to the document date from where the match was found, if no such thing can be found. What was mentioned in the keynote also by Mr. De Witte, we've been talking about training these models, these like SNOMED-aware retrieval models, re-ranker models. How will we train these things? There is no historical data available that's coded for SNOMED CT. And so the solution that we came up with here is that we use open source large language models on site running on consumer grade hardware in each hospital to basically annotate training data for us, right? And the recipe we use for this consists of these 3 steps. We will first extract clinical concepts from document text, and these clinical concepts are really just descriptions of a certain condition and completely detached from SNOMED, right? For this, we use Llama 3.1, 8 billion, because it was 2023. If we were to do this today, we probably would be using something Chinese. But the second step, we will match these extracted clinical concepts to known concept definitions and try to figure out a matching score in terms of cosine similarity between both these representations. And again, the encoder we use for this is this BioLord model. The target for this exercise is the Belgian edition of SNOMED, restricted to the categories of findings, disorders, morphological abnormalities, and procedures. That's altogether some 180,000 concepts. And then finally, at the last step, we're going to triage these definition matches, again, using the large language model that's running on site. So there you have this LLM as a judge mechanism. And so the data that this process generates looks a bit like this. I hope this is somewhat readable. So at the top, you have an example of clinical text that has been properly pseudonymized using this deduced thing. And from this, the large language model would extract clinical concepts, in this case, things like lipoomrichterknie. And there's a matches key that basically lists all the SNOMED concepts that have matched this concept definition with some scores. And additionally, in this data, you can also distinguish which of these matches have been triaged by the LLM. So the LLM says, well, this one looks like a good match. This one, probably not so much, et cetera, et cetera. And the CE score field you can see over there is basically the re-ranker score that the Colbert model would need to try to emulate while training. So we basically generate some 4.4 million of these examples. So the nice thing about this recipe is that the amount of training data you have available, because everybody knows these AI models, they really start working with data at scale, and more data typically always makes them better, is that you're really only bounded by compute and time, because the process of generating the training data is fully automated. Then I don't know how we're doing on time, but
5 minutes.
Okay. So there's from this NLP to OMOP project came 2 other projects spun off. One is a PROSA project, which is led by AZ Oostende, one of the partner hospitals. So in this project, all the hospitals are partner hospitals. And the idea here is to reuse all the technologies developed in the context of this project for detection of clinical indicators for early onset osteoporosis. Right? So osteoporosis is a disorder with a fairly large societal impact. Like there's typically a very large population of elderly patients who are at risk. And at the same time, there is a very simple, non-invasive test for diagnosing somebody with osteoporosis. It's called a DEXA scan. It's like a bone density measurement test. And the setup here is we will use the AI models developed for this project to screen patient reports for these 29 indicators. So these 29 indicators were created by clinicians at AZ Oostende, and they range over things like, fractures, limited mobility of the patient, risk of falling, but also things like alcohol dependence in the past, etc. And whenever a bunch of these indicators have been detected by the model, then this is flagged to the treating physician, and he or she is at liberty to suggest one of these DEXA scans to that patient. There are some MDR issues around the use of AI for applications like this. I think currently the solution that is being looked into is that this will be, because it's something developed in each hospital in-house, the in-house exemption might apply. And so it needs to be validated through some retrospective study, but a full MDR registration process might not be needed. But this is still being looked into. And then finally, there's a last project called NLP OMOP Connect, NLP to OMOP Connect. And this is basically a knowledge transfer project where the technologies and the lessons learned from this project will be rolled out to 4 additional new hospitals to see whether the results can be easily reproduced, and to also increase the community of healthcare organizations that have fair data enabled infrastructure. And I think that is the end of a short introduction to the project. I think there's many more technical things to talk about, but maybe we're sort of out of time. These are the guilty parties. And I think I can take questions now.
Okay, thank you, Sinj. We will now begin the question period. As a reminder, if you're in the room, please use the microphone to ask your question so that everybody can hear you. So we have time for 1 question.
Thank you so much. It's a lot of pressure to be the only question, but I wonder why use the re-ranker where instead you can just rely on this LLM-based judging, which is essentially the thing that you use to train the re-ranker on.
Yeah. So that's the main reason is for engineering reasons, in the sense that if with the current technology and the current hardware available on site in each hospital, using the LLM at runtime for this thing would essentially make the response times very large, because the number of extractions can range in the thousands or tens of thousands. If all these extractions need to be vetted by an LLM running on site, processing time that is usually in the order of seconds all of a sudden goes into hours, maybe days. So that's the main reason.
Right. That concludes our session. Thank you. And to our online delegates, you're welcome to remain here for next presentation in the stream, or you may navigate to another session via the event lobby.